All right. Well, hello, everyone. Welcome to another edition of the Smart Webinar series focusing on machine learning related applications for subsurface problems. Today, we have Dr. Siddharth Misra from Texas A&M University, where he's an associate professor in the Petroleum Engineering Department with a joint appointment in the degree of geophysics. He's going to talk to us about rapid forecasting of CO2 plume migration in varied geological and engineering scenarios utilizing transfer learning. Sid is a petroleum engineer with a very strong machine learning background. He teaches courses in formation evaluation, machine learning, subsurface data analytics. His research focuses on machine learning for subsurface characterization and engineering. He is quite a prolific publisher. He publishes quite a bit in peer-reviewed journals and books, book chapters, etc. Delivers conference presentations, invited lectures, etc., etc. So I'm sure all of that is going to come through with respect to his passion and his understanding and his mentoring of students in combining transfer learning for subsurface applications. So over to you, Sid.
Thank you, Dr. Shrikant, for this nice introduction. Good afternoon to all of you. I am pretty sure most of you are eager to know about the use of machine learning, especially transfer learning. And the whole objective in this particular presentation is improving the speed of CO2 plume simulation. And when we are improving the speed of forecasting, we are also reducing the data requirement and we are reducing the compute needed. In this work, Yusuf Falola, who is a PhD candidate, he's the main person who was involved in all these computational efforts. He was assisted by Andres, who's a master's candidate. So both of them did a lot of heavy lifting in terms of all the compute that is needed. This project is very complex and it's going to get more and more complex as time progresses because we want to make these transfer learning platform applicable to a lot of different geologies and to a lot of different engineering constraints. So with the introduction of the team, I'll just go ahead and I'll start with acknowledgement. Generally, acknowledgement comes later, but for this particular project, nothing could have been done without some of the people who are mentioned here in this particular slide deck. So Akhil Dattagupta, who is a professor in Texas A&M, he got me involved in this project. And Rajesh, Bailan, and Baichang, who are prolific researchers who worked on a similar project focused on machine learning. We got inspired by their work. So the initial 1/3 of this work takes the material and the concepts that were discussed and developed by Rajesh, Bailan, and Baichang. So I'm very grateful to them for helping us get started. Without their help, you will not see what we have done so far. And again, thanks to Carlos, especially Dr. Shrikanta, for guiding us on all the technical aspects. So with that, a quick recap, because we had a demonstration of the power of transfer learning. A few weeks earlier, we showed a small demo. So just a quick recap of that. In that demo, what I showed is we are comparing a machine learning model versus a transfer learning model. I'll explain what transfer learning is in full detail as we go ahead. We did that comparison. The whole objective of this transfer learning is to predict on scenarios that are not seen, that are new, that are uncertain, and to predict. The constraint that is always put is we want to use as limited amount of data as possible. So if you see over here, this transfer learning model is learning from only 20 samples. These samples are simulation runs. So from 20 simulation runs, it is learning to predict CO2 plume propagation. And we are comparing that with a machine learning model that was trained on 72 simulation runs. And if you see the type of geomodel realizations, the number of injectors, their location, we are in this particular example, we are changing the locations. We are not keeping it fixed compared to the machine learning model. So the whole objective is how can we predict for uncertain situations? And in that work, which I demonstrated, what is the main takeaway that we came up with is a CMG simulation run of CO2 propagation over 30 years of injection and 50 years of monitoring takes 40 minutes. Compared to that, traditional machine learning model developed on limited scenario will take 12 seconds to forecast. And a transfer learning model, which can handle a lot of uncertain situation, takes 7 seconds. So that was the main takeaway in that earlier work. So what I'll show you today is a brand new effort that we have put in, and will show you some more comparison that will kind of validate the need of transfer learning if we want to boost CO2 forecasting in the subsurface. So the first concept that I want to introduce to all of you who are here, because all of you are experts at a lot of different disciplines, and maybe this concept of Fourier neural operator is not relevant or important for you. So let me just introduce this particular concept, Fourier neural operator. And we are using this operator for rapid simulation. Why do we need rapid simulation? Because we want to make engineering decisions. To take engineering decisions, we need to see a lot of different probabilistic assessments. We need to perform inverse modeling. So for all that, we need rapid simulation. Two traditional approaches are shown over here. The first one, which is called finite dimensional operator, an example of that will be a convolutional neural network. So this operator, this finite dimensional operator, it maps a Euclidean space from one Euclidean space to the other. The problems are it gets into overfitting, it needs a lot of data sets, and it can only predict for specific temporal and spatial meshes on which it is trained. So this is the traditional CNN type of approach that can be used for rapid simulation. The other approach, which is generally called the physics constrained or physics informed approach, it tries to parameterize the solution function using a neural network. If you look at the compute, to the best of my knowledge, the compute tends to be similar to a numerical solver. Uh, some of you can correct me, but based on my limited understanding, when we try to forecast using these neural finite difference learning, we don't get a boost in computing. And it generally requires separate training for new instances. It cannot scale that well. So compared to traditional neural network-based approaches for rapid simulation, what we are using is a neural operator. Uh, a neural operator technique has been developed in 2020. I have the citations in some other slides, but let me just introduce what this operator does. So what is an operator? An operator is a functional mapping between two distinct spaces. It acts on a set of samples in one space and transforms those samples into the other space. So that's an operator. When we try to learn the operator using neural networks, that is called the neural operator. It learns the mapping between input coefficients and the output solutions. I will show you an example which will clarify what I mean by input coefficients and what I mean by output solutions. But the beauty of this output solution is it can take care of a family of partial differential equations. Now, once we have trained a neural operator, when we provide a given initial condition or the boundary condition, it can directly output all the solution. So that is a neural operator. And let me explain what I mean by input coefficients and the output solution. So what you see over here is a set of inputs that is provided to a neural operator. So input coefficient refers to the field variables, permeability in X direction, Z direction, porosity, perforation of the well. And then there are some scalar variables. So all this information goes into the neural operator as a set of channels. And what we can predict is how the fluid evolves as a function of time, how the pressure builds up as a function of time. This particular slide that I have taken, or this particular figure that I have taken, is from Wen et al. 2022. So there they show the use of Fourier neural operators for a very specific task. And we have done something similar in our demonstration. So Fourier neural operator. So this word Fourier, how does it help the learning of an operator. If we just look at 1D Fourier projection, for any given signal, we can break the signal into a combination of sinusoidal waves. So this is 1D transform. A 2D transform will work on an image, and what it does, it converts this image into a collection of sinusoidal planar waves. Now, what I'm showing you is these three planar waves exist in a specific angle, but we can change the angle as I show over here. And then when we mix, we can create uh, more perturbations, which can then be inverse transformed to obtain new images, new 2D distributions. So the core of a Fourier neural operator is the 2D transform. These are some examples of 2D Fourier transform for a given spatial distribution. When we perform this transform, what we get is two coefficients for two distinct frequencies. Similarly, here also we get two distinct frequencies and some magnitude associated with it. That is the starting point. Using Fourier layers will convert a given input coefficient into its Fourier representation. So given any set of inputs, which is a permeability, porosity map, or where the injection location is, where the production location is, any 2D representation that we can provide as an input goes into this Fourier transform, and we obtain the planar representations, planar wave representations of the input. Then we have this neural network that learns on the Fourier coefficients. The neural networks here don't learn on the original input space. What they learn on is this planar wave representation of the original input space. What they are learning is to generate a set of planar wave representations that can later be inverse transformed to generate the entire output solution. So the output solution is how does this fluid propagate in this subsurface in a 2D or a 3D representation. So it's a very powerful technique where the learning takes place in the Fourier domain, and we involve the transforms, both inverse and the transform in the initial layers. So what I'm showing you here is a Fourier layer, which is the core of a Fourier neural operator. So this operator can be simply represented as a set of input coefficients that is first lifted into a high dimensional representation. So this is a set of neural networks that represent the input in a high dimensional space. Then we have a bunch of Fourier layers that works on this high dimensional representation. Then there is another network that brings all this information down into a lower dimensional representation, which is the output solution that we need. Inside each Fourier layer, as I mentioned, we have a transform followed by removal of high frequencies, and then an inverse transform. There is a ReLU or a nonlinear activation function that ensures that this entire Fourier neural operator can learn all the complexities present in the data. So with that introduction of Fourier neural operator, let me give you a quick overview of what we want to achieve using Fourier neural operator. We want to rapidly simulate the CO2 storage in a subsurface. So for this work, we have a set of input coefficients. These are the permeability, porosity map, the location of injectors, the location of the producers, and then the time steps at which we want the output solution. What are we predicting? We are predicting pressure and saturation evolution in the subsurface in an entire three-dimensional geomodel using four distinct Fourier network operator models. So we are creating four models. One model that specifically focuses on predicting the saturation during the injection of CO2. The next one takes care of the pressure during the injection. And the other two look at post-injection phases of saturation and pressure. The reason we are creating these four models is we tried a lot of different permutation and combinations, and inspired by the Los Alamos National Lab work that was done in stage one, we also agree to what they presented 2 years back, which is there is a need for having 4 distinct models to take care of each of these regimes, because each regime is distinct. So with that, let me show you how our Fourier neural operator looks like. For a given set of inputs, we want to predict how the pressure and saturation will evolve. We can predict the pressure and saturation evolution in the entire lateral layer, because it's a sinusoidal representation that can be inverse transformed. For this entire effort, we need around 5 million model parameters. We tried a lot of different loss functions, a lot of different hyperparameter tuning. It was a very computationally intensive work. The results that you'll see has a lot of computation and a lot of data management that was involved behind the screens. For learning, we need simulated data sets. Without the data sets, we cannot learn, right? So what is the data set we are learning from? Let me talk about that. We are creating 2 distinct data sets. Dataset 1 for machine learning model 1, dataset 2 for machine learning model 2. This model, machine learning model 1, will be integrated with transfer learning. So we will improve this machine learning model 1 predictions by invoking the principles of transfer learning. So that's why we have this model. And once the transfer learning model is created, we'll compare the performance of the transfer learning model against the machine learning model 2. If you look at the properties of dataset 1, what is there in the dataset 1? There are 90 samples. Out of the 90 samples, which are simulation runs, each is a simulation run. So out of those 90, 70 will be used for training and learning for the machine learning model. The rest will be used for validation and testing. This is the porosity range, permeability range. In this dataset 1, we have very specific geological realization, P25, P55, and P75. Number of location is fixed for injectors and producers. The production constraint is fixed. There is 5 distinct CO2 injection masses that these simulations have. And the injection split is also varied between all these different 90 different samples. So if you look at dataset 2, which will be used to compare how good is our transfer learning compared to a traditional machine learning, that has 180 simulation runs. Out of 180 simulation runs, 110 will be used for training. It has 5 very different geological realizations compared to what is there in dataset 1. The location is fixed, producer location is fixed. It is taking into consideration 10 different rates. Only the initial and the end rate are the same. The remaining are different between dataset 1 and dataset 2. And in terms of split, we try all these different split. So all these different combinations that you see in blue creates one unique realization. And each unique realization goes into this 180 samples that we'll use for training. So each sample that you're seeing is unique in what it contains. This is a SACROC geomodel that we're using, which represents 8.2 kilometer by 4 kilometer by 0.3 kilometer. It is discretized using 36 cross 16 cross 25 grids. And in all the simulations that you'll see going ahead, you will see 30 years of injection followed by 50 years of monitoring, which we also call the post-injection phase. These are some of the geomodel realizations that we're using. The ranking scheme was already developed in stage 1, so we are using that ranking scheme to select these realizations. This is a traditional CMG simulation. No machine learning has been done here. This is how the dataset looks like, and the machine learning methods will learn from this dataset. So the dataset 1 pressure, dataset 2 pressure. There are injectors over here, injectors over here. I'm not going into these simulation results because we have spent a lot of time. These simulation results are working fine, and we have cross-checked with previous stage one work. So I'm not going too much into detail of this. So once the data set is ready, the next is to train the Fourier neural operators and then start predicting. And what I'll show you next are some predictions compared to the simulations. This is CMG simulation for dataset 1, which is used to create machine learning model 1. This machine learning model 1 will be converted into the transfer learning model. This is CMG simulations that is used for learning. This is predictions, and this is the error. And error is represented here as relative percent. It's a relative error. When we see all this thing to be green, it's very encouraging, which means our model, our machine learning model 1 has learned how to simulate, and it has learned how to simulate over time and over various layers. What you see here is a snapshot at 30th year, which means end of the injection. This is another sample, which also shows very low errors of the FNO model that we created. This is saturation. Saturation tends to have a higher error over. For pressure, the error is as close to zero, but for saturation, the errors at some points are close to 10%. We have not spent time on focusing on how to reduce the error on the saturations. This is a pending task. But overall, we are able to predict the saturations. The error tends to be between 8% to 0%. So that's the error that we have in the saturations. So now I'll talk about transfer learning. Why are we using transfer learning? The reason is we want to show the power of transfer learning in terms of reducing the compute time, reducing the compute requirement, reducing the storage requirement, and increasing the speed of forecast. So that's the whole objective. So what is transfer learning? Simply put, we want to reuse or repurpose a model trained on a source domain slash task. So domain and task, they're two different things, and I'll explain the difference between the two. But we want to take this model from the source domain slash task and use it or repurpose it for a target domain or task. We want to achieve faster training. We want to achieve better accuracy. And the problem that we are solving, which is trying to simulate, is a very complex problem. It's a very high dimensional problem. So any means by which we can increase the training speed is encouraged, and transfer learning provides this means to increase the training speed. So let me try to give some examples, and that will help you appreciate transfer learning as a concept even better. So as I mentioned, there is something called a domain, and then there is something called a task. So in our work of predicting CO2 simulations, our task remains the same, but the domain changes. What do I mean by domain from our point of view? From our point of view, domain means all the different geological realizations, all the different engineering realizations. So that's a change of domain. As the domain changes, can we still perform the task, which is predicting the pressure and saturation? So let's look at this particular option here, which is the domain stays the same. There's no change in domain, but the task changes. An example of that will be playing piano. So use of knowledge of a classical piano to help play a jazz piano. So the domain stays the same, which is piano playing, but your task changes from classical to a jazz playing. Now, in terms of a change in domain, knowledge of driving will help you bike. So if we know how to drive a four-wheeler, we can ride a two-wheeler. So that's a domain change, but the task remains the same, which is driving. If you look at E, which is a combination of change in task and change in domain, that is knowledge of driving will help you win a racing video game. So here the task and the domain both change. Going ahead, If you look at C, which is dissimilar domain, but the same task. So dissimilar domain and same task. Example would be knowledge of solving math problem will help you solve physics problems. Domain change is from maths to physics. The task is solving problems. If you look at G, which is dissimilar tasks and similar domain, English writing skills will help English speaking skills. The domain is still the English language, but the task changes from writing to speaking. So you take something from writing and use it for speaking. So with that example, hopefully all of you will appreciate how transfer learning can help us uh, adapt to change in domain while our tasks remain the same. So how can we achieve transfer learning? There are a lot of different approaches. The two approaches that we are using in our work are fine tuning and feature extraction. So what is fine tuning? We have a model that is already ready. Let's say the model has 10 parameters that it has learned from the source domain. Now we want to take it to a target domain. So when we take it to the target domain, we take all those 10 parameters and refine those 10 parameters. So instead of randomly initializing the parameters, we refine the learned parameter. That's fine tuning. We use this in our work. The next one is feature extraction. An example of that will be if you can detect English language alphabets, you can detect, let's say, Greek language alphabets. So we have a model that has learned how to detect English language alphabets. We use a part of that model that has learned to detect those alphabets into a Greek language detection model. So that's feature extraction. We also use this approach. Next, we have domain adaptation, multitask learning, and zero-shot learning. If you're interested, we can talk about this later on. In multitask learning, we simultaneously train a model to perform two different tasks, spam detection in English and spam detection in Russian. So two different tasks, but they are trained together. There's an inductive transfer of knowledge between the two tasks. Zero-shot learning, you have a classifier that can detect a bird. A new bird species arrives. So how can you detect this new bird species? If you can detect it, that will be called a zero-shot learning. So these are very interesting concepts, and what we are using are the basic foundational transfer learning. Maybe these different tasks can also be explored going ahead. This is what I meant by a feature extraction for transfer learning. English language detection model can be used for Greek language detection model. All you have to do is take some features from the early part of the network and use it for your target domain. I'll skip this and I'll move on to the results. So where I'll show you how transfer learning helps us achieve rapid CO2 storage simulation. So we still use Fourier neural operator. That's our foundation. That's the core machine learning that we use. This core machine learning will be improved further by adopting transfer learning techniques. To demonstrate the power of transfer learning, I take machine learning model 1 that is trained on dataset 1 and I improve it for a different dataset. And for improving it, we are using transfer learning. And in transfer learning, we are using both the fine tuning and the feature extraction capabilities. So with just 30 simulation runs, we will learn how to predict CO2 storage for a different realization that was never seen in the base um, model creation. And we will handle different injection rates that were never seen in the base model. The base model was learned from 72 simulation runs. The transfer learning that we are invoking will be done on 30 simulation runs. One thing we've ensured is we have ensured that we keep a lot of validation samples and testing samples so that we can truly validate the power. The focus is to learn from less and ensure generalizability. And that's why we have a lot of validation and testing simulation runs. This is a comparison between dataset 1 and dataset 2 in terms of the realizations that were used. As I mentioned, we are using two different techniques. This is method one, which is the feature extraction, where we take a part of the network that has learned on dataset one and we freeze it and we learn a different, the later parts on dataset 3. So this part learns from dataset 3 and this part over here has already learned from dataset 1. So a combination of these two is what is called the implementation of transfer learning on the Fourier neural operator. This is method 1, feature extraction. In method 2, we train the model on dataset 1. We get all the parameters that can perform really well on dataset 1. These parameters are refined and retuned for the dataset 3. When we do that, the number of parameters that we are tuning stays the same as the original set of parameters. So we try both of them, and based on our experience, both of them perform similar in terms of their accuracy and speed and all that. But again, we have to spend a little more time to truly evaluate the difference between these two methods. This is a comparison of transfer learning predictions, which is in the middle, versus true simulation runs from CMG for various layers at 30th year. I'm showing you two distinct samples. They have different injection rates. They have different geomodel realizations. So for these two samples, pressure has a very small relative error, which is very encouraging. Saturation tends to have errors between 0 to 10%. I will show you another plot where I'll show you the errors in a little more detail where you can appreciate what's going on. This is again another pressure at 80th year. So this is during the monitoring phase post-injection. Pressure plumes are being predicted really well. Saturation has problems in terms of the error being between 0 to plus minus 10%. So we have to figure out ways to improve saturation performance. So this is at a given cell. So we have selected one cell and we want to see how the error for that cell changes with time. And we are looking at pressure during the injection phase. So this is the error, relative error for that cell. And as the time progresses, the relative error decreases. This is another cell. Again, we are looking at the pressure. Pressure decreases as the injection continues, which is very good. That's what we want. As injection goes on in the reservoir, we want to have better control on the pressure profiles. This is, again, pressure, but during the post-injection. We are looking at 30 years to 80 years. Very small error. Monitoring performance is much better than the injection performance. During injection, there's a lot of dynamic changes, and our post-injection predictions are much better than during injection. In terms of saturations, initially, there's a lot of error in the saturation at that grid location, which is the 10th there's the 24th layer. But as the time progresses, the error kind of stabilizes. Again, we see the same thing, large errors during the early time, and then the error stabilizes. How to reduce this error in saturation, that will be our focus going ahead. But for post-injection, our errors for saturation are much better, between 0 to 8%, a bit more manageable than what you saw during injection. So let me show you some concluding slides, and then we can open up for Q&A. So here, we'll compare in terms of numbers between what we get from transfer learning and what we get from machine learning. Just as a reminder, this transfer learning model is a refinement of the base machine learning model 1. Machine learning model 1 was trained on dataset 1, which was very different from dataset 3. And that model was refined into transfer learning model, and we'll compare machine learning model 2 against against the transfer learning model. Between these two data sets, a lot of things are very, very, very similar. For example, dataset 3 is a subset of dataset 2. Everything that you see in dataset 2 is present in dataset. Sorry, the other way. Everything that you see in dataset 3 is present in dataset 2. Dataset 3 is a subset of dataset 2. On dataset 2, we train machine learning model, which requires 110 simulation runs. And we'll compare that with a transfer learning model, which requires only 30 simulation runs. The total mass injected is different for dataset 2, dataset 3 as compared to dataset 1. So both of them, they are similar to each other, but they're different from dataset 1. The same thing over here, the geomodel realization, they are similar between these two, but different from dataset 1. So now let me show you some numbers that will, okay, I have a chart here. So this is the mean relative error for various realizations. Mean relative error for various cells. And we are showing a histogram. And the good thing is both the transfer learning and the machine learning model too, they kind of overlay on top of each other. They have similar performance of accuracy for saturation and for pressure. There's a mistake here. This pressure should have been here and saturation should have been here. I think there's a mistake over here. Going ahead, we are comparing transfer learning with the base machine learning model 1 on which it was improved. So again, what we are seeing is with very limited amount of data, the performance is very similar to base model 1. Same here, the performance is very similar to machine learning model 2. So it's a very nice comparison between what we truly get out of transfer learning. So the whole objective of transfer learning is with limited amount of data, with limited simulation time, limited data storage, we can achieve similar accuracies in saturation and pressure. So if you look at the forecasting, it takes us 47 seconds to forecast as compared to machine learning model 2, which takes 107 seconds to forecast. CMG takes 40 minutes to forecast. So compared to 40 minutes, machine learning can help you do the same task for one simulation run in 107 seconds. And transfer learning implementation will help you achieve the same forecasting in 47 seconds. If we look at the training time, approximately speaking, because there was some challenge here, so that's why I've used this approximate symbol. So approximately speaking, machine learning model 2 took us 3 hours for training. Compared to that, transfer learning just takes 0.5 hours, which is very encouraging. So it's 6 times smaller, which is very good. The data storage is 1/3. Simulation time is 1/4. So in all these different metrics, we are achieving a very good, very encouraging performance with transfer learning. So with that, let me tell you the next steps, and then I'll stop here and take some questions. So where are we heading with all this effort? Whatever we have done so far is setting the stage ready so that we can go to the next step. And in our next step, the first objective is we want to handle any geological realization with any injection rates. So this is uh, the most important task that we are going after. How can we create this model so that we can handle any realization and any injection rate for all these different injectors that are there. Next, we want to take whatever we have learned here and improve it for handling any injection location. So now injection location doesn't need to be fixed. Over here, injection location is fixed. The only thing that is changing is geology and injection rates. Once we handle that, we want to tackle any injection location. And once we handle that, our end goal will be to take care of any injection schedule for any injection location at any injection rate for any geological realization. So that's the whole goal. Let's see if we can achieve this or not. With that, thanks a lot for your attention. That's the end of my talk.
Folks, feel free to unmute, raise your hand, or put questions in the chat. And we already got a hand raised from Syed.
Oh, okay. Just a quick question. I guess in the previous slide said, great presentation, by the way, at least for to understand how the FNO works. On slide 54, when you are doing the comparison, as far as the number of the data is used and also training time. So in reality, based on what you presented, for the transfer learning model, you already have to rely on the things that you have got from it, the ML model 1. So isn't it like the training time, for example, has to be like 0.7 hours plus the 0.5 hours that you spend on that one?
I agree. I agree with you on that. So
Okay.
this TL model, all these numbers that we're telling is just specific to this upgrade of the base model to a model that has invoked transfer learning. But truly speaking, I agree with I agree with you that this too will get added. This too will get added. Um, uh, let's see if Yusuf and Andres can comment something on that. If not, then I'll come back. Yusuf, Andres, any comment on the question?
Could you please repeat the question because I was?
Oh, that's fine. That's fine. So yeah, what I meant is what Said is mentioning is truly valid, which is we need to add these things.
Which is fine. I'm just trying to understand. Yeah.
So the ML1 is the base model in this case. So we assume that has been trained, so it's not really coming into play when we do the transfer learning. So for the transfer learning, we are only using the trained model, which can be done by someone else, even if not us. So as a base case, so then we only have our own data sets, which is the 30 in this case, and then we apply transfer learning methodology to train on it. So we are then comparing the results of the transfer learning to a case. Let's say we want to actually do everything from scratch when we don't have a pre-trained model. So we need this much data, which is the ML model, to achieve the same goal that we would have achieved using this TL model. So that's the whole idea.
Say one thing that I wanted to kind of summarize, and I was not getting that line. So my summary is we don't need to create a model from scratch all the time. We can always take help from previous models. So that's the power.
Yeah. No, I appreciate that. And actually, it's interesting. I just wanted to clarify that point for myself.
Yeah.
And I guess the other thing is, I don't know if you look at I'm not sure how these simulations compare to what we did in phase 1 of a smart for SACROC. Is there any overlap or not? But I don't know if you had a chance to compare the forecast times for that, because I remember in phase 1 we had some. I wasn't a part of SACROC model team, but there were some statistics reported on that as far as how fast they can do it for forecasting and things like that, the accuracy and things like this.
Yeah, so we took everything from stage 1 for the SACROC model, and on our computers, the computers that we are using, this is what we obtained in terms of how much time and all that. So we redid all that was done in stage 1. We redid it, and this was the previous work that I showed in the hands-on meeting. Yusuf, any comments on that?
Okay, in relating to the phase 1, for the phase 1, we also noticed that the data that was used had some repetition. So in our case, there's no repetition, and I think the accuracy is also higher than the accuracy of those from phase 1 when we compare them, because we got the data from those who worked on the phase 1.
And for our phase one reference, as I mentioned right at the beginning, this is the work that was done by this amazing team from Los Alamos. So we relied a lot on getting started. So we always referred to their work and we just kept on improving.
Yeah, I can send you the reports from the phase one that NETL and I guess a bunch of other teams also tried the SACROC. And from what I remember there were some good results with even less than a second forecast time from the table that I have in mind. But I'm not sure what kind of resources they were using, for that. So I'm not gonna hold you guys on that because they may have been using, some supercomputer or something. But anyways, yeah, that was my question. Thank you.
Thanks, Syed, for this good questions. Thank you.
Our next question came through in the chat from Kyung Min. Is transfer learning requiring pre-training plus new training data? And if so, comparing with the ML model 2 of 110, total training data set size looks similar between them. Is that right? And follow-up question, does this model depend on the number of grids?
Yeah, so the first part of the question is very similar to what Saeed asked us. And I'll go back to this final slide. Can transfer learning boost CO2 forecasting? Yeah, so the first part of the question is, yes, it is very similar, but the whole objective here is we don't need to do anything from scratch. We can always take benefit from pre-trained models. Now, the beauty of Fourier neural operators, to the best of my knowledge, which we have to implement more to be truly sure about, is the predictions are independent of the spatial and temporal mesh that is used. Because at the end, what we are doing is we are performing an inverse Fourier transform and we get this global function. And because it's a global function, we can scale the model to different spatial and temporal meshes. And this is one of the powers of Fourier neural operator.
Eric, your hand is raised.
Yes, first of all, I want to say I'm very impressed with the presentation and what it taught me. So my questions are kind of come from my experience and also what you just taught me this afternoon. Well, how would you implement, for instance, pressure transient analysis if it was available in this? And why did we choose Fourier instead of something that's more sensitive to radial flow, for instance, like Laplace approaches?
Got it. Got it. Great question. So I'll answer the second question first, which is why Fourier? And maybe for that, what I need is to go to a backup slides. This one over here will help me explain that. So generally, in a traditional rapid simulation effort, convolution neural networks were widely used. And what convolutional filters they learn is local representation. They learn edges, the shapes, and all that, but mostly the local features and how these local features translate and scale across various inputs. What the Fourier filters are learning, they are learning a global representation. They are learning global sinusoidal functions that are better to represent a continuous function, like a evolution of a CO2 plume in terms of saturation and pressure in the subsurface. They can capture global spatial and temporal correlations. So that's my first part. It's as to why we should use a Fourier filter, or why should we use this method over convolutional. Answering that second part a little better is we didn't develop the Fourier neural operator. The method was developed in 2020. I have cited it in one of my slides. I can give you the reference further. That particular approach is based on the hypothesis that any input can be expressed as a sinusoidal planar wave. Any input that you give after Fourier transform can be represented in this sinusoidal manner. And now the learning is taking place between the input domain and the output domain in terms of the Fourier coefficients. And once we obtain one representation over here, that can be inverse transformed to obtain the entire output solution. That's our end goal. Can we replace the Fourier transforms over here with wavelet transforms? I think we can, because at the end, the approach will be to relate the wavelet coefficients. Can it be replaced by a Laplace transform? I think it can. So great question, but I don't have a final answer on that, but something for me to think after the meeting. And regarding the first one, which is pressure transients, yes, pressure transients can also be taken care of. What we are doing here is we are trying to take in these inputs and generate a really complex, very high dimensional solution. And the solution is how the pressure and saturation are evolving. We can replace this output with the change in the pressure at the borehole or the wellhead pressure. We can definitely replace the outputs with something more simpler, just as a time series, and we can still achieve this mapping between the input space and the output space. So your question, if we replace it by pressure, it will be a slightly simpler problem compared to what we are trying to solve here.
And have you considered how you would integrate, for instance, microseismic background energy changes or DAS information?
I have not thought about that. I would love to talk with you and get some inputs.
Thank you.
Thank you very much.
And I want to emphasize it was an excellent teaching. I learned a lot. Thank you.
Yeah, I prepared this presentation in the last minute, but this is the first time I'm presenting this entire work. So thanks a lot for all your patience and good questions. First presentation is always a little bit challenging. It still needs a little more refinement.
Jared, your hand's up.
Yeah, thanks. Also, I agree. This was a great talk. When I was looking at so you had a slide showing dataset 3 compared to dataset 1. So, dataset 1 being used to construct like the base machine learning model, and dataset 3 being the case that you would like to transfer to. In terms of the domain and task kind of separation you had before, I guess I would think then that the task here is the same because you're trying to predict pressure and saturation, and it's the domain that's shifting slightly.
Yes.
So the main differences between the base case and then what you're transferring to is really a change in these geomodels and I guess in the observed total CO2 mass injected. But in terms of the mass injected, I mean, these values are really, they fall within the same range of injected masses from your dataset 1, which I would expect dataset 1, for example, to be able to interpolate to one of these injection rates for the geomodels, 25, 55, and 85. So I guess is the transfer learning in this case, would it be right to say that really it's transferring from these 3 geomodels on the left to the 2 on the right? That's where the transferring is occurring?
Yeah, you're right at everything that you pointed, everything that you said. I don't have any objections to that. I completely agree with that. We have tried transfer learning where the base model has fixed locations and the target domain has variable locations. We have tried that. And we have also tried predicting outside the range. But again, due to limited amount of time that I had, and I was not able to bring in all that information. But what we are observing consistently is if we change the locations, these transfer learning still predict pretty well. When we try to predict outside, a little outside, they still predict pretty well, but I don't have any slide to show you those efforts. Maybe a little more time will be needed to get those. But before I leave, I just want to bring your attention to the recap that I showed. And in that recap, the beauty was we handled uh, completely different injection rates, but it was within a particular range. So the base machine learning model only saw 2 rates, while the transfer learning saw many more rates, 45 different rates. It showed 45 different locations of the injectors, which were not seen in the base model. So there also we performed really well.
Yeah, okay, and I guess the injection locations, you had that as one of your inputs, at least on one of your slides.
Yeah, in this demonstration that I showed you.
To me that works that well. I mean, that's good, because of course that's one thing we're concerned about is changing injection locations. But I guess, yeah, doing this sort of like a dimension reduction down into this Fourier space does seem to allow you to do some of that transfer. That's nice.
Yeah, and as you know, this is a pretty compute heavy work where we have to do a lot of data management. So when I was asked to present this, I didn't have sufficient time to bring in everything that's important. But next time when I will present this work, my focus will be to show all of you a little more of how we handle 45 different locations, very different rates. So we'll expand all that as we progress. Okay. Yusuf, any comments on that? Or maybe Andres?
Well, just to add to what you have said, so what we did this as a step 1 of the transfer learning, and if you are listening to the next step, so we want to build on this so that the next case we have variable injection rates, and the case after that we also have the start-stop schedule change, because we know in reality you can't continue to inject forever, so there will be some stop and some start. So we are trying to also include that in our in the transfer learning. So we are trying to get a model in first step, carry that model to the second step, and then to the third step, so that the model learns as we move ahead in the steps.
Yeah, and one thing that I would like to point out here is we are not involved in the phase 1. We got involved in phase 2. So we started actively working on this with Yusuf, me, Andres, starting July. So initial 5-6 months were all about exploring, trying different things. And now we are kind of getting into that pipeline, starting from what is important and then slowly moving into more and more complexity.
So it's 1 minute past the hour. This looks like a very fun discussion period that I'm sorry to be cutting short, but we need to head out to other things. So Sid, once again, thanks for taking the time and for a very nice, enlightening presentation about the concepts and also the results, which look very encouraging going forward. Those of you who had any questions, feel free to reach out to Sid, and we'll see you again next time. So thanks.